Hi everyone, I'm James Han. In this presentation, I'll be walking through my Physics 2211 Lab 3 project, which focuses on modeling gravitational motion and determining the mass of black hole using Newton's law. The lab had two main goals. Part 1 was about finding the mass of black hole by analyzing orbital motion data. Part 2 was about simulating a spacecraft's motion under the gravitational forces from both the planet and its moon, basically trying to find the right standing velocity for a stable figure 8 orbit. The two key physics ideas behind this lab were the momentum principle and Newton's law of universal gravitation. According to Newton's second law, the net force on an object equals the rate of change of its momentum. In space, gravity is the only significant force, so every change in motion comes directly from gravitational attraction between masses. By combining these principles, we can relate how velocity and momentum evolve under gravitational influence. The momentum principle: F net equals momentum over time. Momentum equals m times v. Velocity equals position over time. Final position equals initial position plus velocity times time. Centripetal force equals mv squared over r. F net equals momentum over time. Takeaway: gravity is the sole force influencing the object. All objects are treated as point masses. The black hole and planet remain stationary. The time interval between data points is uniform. Newton's law of gravitation and Newton's second law apply at all times, and the system is considered isolated. Mass of black hole is 1.39 times 10 to the power of 34. Initial velocity of the ship, negative 4.3 times 10 to the power of 4, 4 times 10 to the power of 5, and 0. In part 1, the system we focused on was the star orbiting the black hole. The black hole acted as surroundings, providing the gravitational force. We used the relation P equals mv and tracked how the star's momentum changed over time. By finding dp over dt, we determined the net force and then solved for the mass of the black hole using Newton's gravitational formula, F equals g times m1 times m2 over r squared. From the data, the calculated mass of the black hole came out to be around 1.23 times 10 to the power of 34 kilograms, which is consistent with a supermassive black hole range. The assumption here was that both the star and the black hole acted as point masses, and the black hole stayed fixed while the star orbited. Gravity was treated as the only force, and time intervals were constant to simplify the computation. For part 2, we expanded the model to include a planet, its moon, and a spacecraft. The planet and moon provided gravitational forces on the ship. Our goal was to tune the ship's initial velocity to create a stable figure 8 orbit where it loops around both bodies without crashing into either one. The system was a spaceship, surrounding was the planet and the moon. In my computational run, the spaceship's path came close to the moon's orbit, but didn't fully form the figure 8 pattern. It remained near stable but slightly off. This shows how sensitive orbital systems are. Even a small change in starting speed or direction drastically alters the outcome. The sources of error. A few key assumptions were made. All bodies were treated as point masses. The planet and black hole were kept stationary. Simulation ignored external effects like tidal forces or relativity. Major errors sources included round-off errors due to limited precision and simplifying physical assumptions that reduce realism. What if and what does it mean? How does the net force and its parallel and perpendicular components differ from the change of momentum and its parallel and perpendicular components? According to Newton's second law, F net equals dp over dt, the component of the force parallel to the momentum vector changes the object's speed, while the perpendicular component only alters its direction. In practice, slight variation may occur due to approximation in computing velocity and acceleration. In this lab, dp over dt can be used in place of F net since it allows us to determine mass directly, whereas F net requires the mass to be known beforehand. If you wanted to predict the motion of the entire system, what would you need to include in your computational model? All bodies are treated as dynamic masses. The model must account for the gravitational interactions among the planet, moon, and spacecraft, incorporating each other's mass, position, and velocity so they can mutually influence each other's motion. According to Newton's law, their positions and velocities should update continuously over time. In this system, the planet's gravity would be the dominant force, as it has the greatest mass and gravitational force is directly proportional to mass. Thank you for watching. It was James Ton presenting Physics 2211 Lab 3.